Hi everyone, welcome and thank you for joining us for our 10th Learn From Home Live. Hard to believe that we're already into the double digits. My name is Rose and I am the Marketing and PR Coordinator here at Ocean Sonics, and I am joined today by Matt Dempsey, the Sales Manager of Commercial Business at GeoSpectrum Technologies. Hi Matt.
Hey Rose, how you doing?
Lovely, thanks. And yourself?
Doing great, thanks for having me in.
Oh, we're so happy you could join us. And for those of you who have joined us for our previous sessions, you will know that we regularly hold staff learning sessions at our office. And this is where our teammates share their expertise with the rest of our crew. And now, because so many of us, and not just Ocean Sonics, are working from home, we wanted to share our learning sessions with you. We'll be doing these live sessions regularly, so please keep your eyes on our social media channels. This is where we're going to share all the details such as upcoming topics and sessions. If you missed any of the previous sessions, don't worry. You can find them all online. We record them all, and they live on our YouTube channel, so you can visit or revisit anytime you'd like. So for today's session, it will also be recorded and shared online, so don't worry if you missed something or would like to watch it again. So for everyone joining us today that's unfamiliar with Ocean Sonics, we're an ocean acoustics company, and we're based in Truro, Nova Scotia on the east coast of Canada. We created the IC Listen, which is a real-time smart hydrophone. This is a tool that's used to collect ocean sound data, and what makes it so special is that this hydrophone processes that data in real time, so you can actively listen while the sensor is deployed. Something that's really important to Ocean Sonics is supporting our local ocean tech community. The east coast of Canada is a hotbed of ocean tech activity, and some of the best tools and technologies are coming out of our region. Working with GeoSpectrum Technologies, based in Dartmouth, Nova Scotia, was a natural choice for us when we were looking for acoustic sensors. Matt represents GeoSpectrum as part of their sales team, and I have been lucky enough to work with Matt on a number of occasions and hear him speak about underwater acoustics and transducers. So I know today's session is going to be a great introduction to underwater sensors. Thank you again so much for joining us today, Matt.
Yes, thank you for having me. I'm really excited.
So after Matt finishes his presentation, we will have a Q&A session. So if you want to know some more detail about what we cover today, just leave us a comment on our live stream and we'll try our best to answer it after the presentation. So Matt, why don't you take it away?
I'll do that. Thank you again. I'm really happy to be a part of this 10th anniversary edition of your guys' webinars. So, thank you again for the invite. It's much appreciated. So as Rose mentioned, today I'm going to be talking to you folks about marine acoustic transducers, sound, how it's used in the ocean for applications of sonar, active passive sonar, what piezoelectric ceramics are, and how they actually put sound into the water and get sound out of the water so you can process data, learn more about the environment, and whatnot. So for those of you who don't know, we're actually located just down the road from Ocean Sonics. We're right on the coast in Halifax, Nova Scotia, Burnside technically. We're really strategically placed in Nova Scotia for the industry. There's a lot of exciting things going on in the industry right now in the region. Of course, we're very close to the eastern seaboard of the United States. The Ocean Supercluster Project, if you don't know anything about it, I suggest you do some reading on it. It's a initiative that's being put forward by the Canadian government. So it's a government, academia, and industry combination. There's a number of prime companies that are basically helping to further the technology and to bring more business into our region. It's headquartered in St. John's, Newfoundland, but there's a lot of activity happening here. Most of it around COVE, which is the Center for Ocean Ventures and Entrepreneurship, which is a ocean small business and startup incubator. Our access to the ocean, our access to the Bedford Basin, which has 70 meters of water in certain places, is very strategic as well. So we have companies from around the world, institutes like Woods Hole Oceanographic Institution, Scripps Institute of Oceanography, that actually come to Halifax to do their integration testing of their systems. And we're really proud to be a part of that. And of course, we've got the Bay of Fundy as well, that has the fastest rising tides in the world. There's a lot of energy we harness there, and it's a huge topic right now in the industry, basically trying to figure out how to harness that energy without destroying the equipment that's in there, because the power behind the water that rushes in and out of there is substantial, to say the least. So for those of you who aren't in this area right now, there's actually a fog bank that's sitting off the coast of, just off the coast of Halifax, and you can see it when you're driving across the bridge from Dartmouth to Halifax or vice versa. And when in the morning we wake up and it's on top of our heads, and in the evening it drops in on us as well. I wouldn't be a maritimer if I didn't find out a way to complain about the weather at least once while I was doing this presentation. So for those of you who aren't here, you're lucky that you're not, because it is really humid. I'm lucky I'm in an air-conditioned room right now. So GeoSpectrum Technologies, what do? We do quite a few things. We predominantly design and manufacture marine acoustic sensors and systems. So hydrophones, sound sources, active and passive sonar systems for navies, and we predominantly cater to the defense industry. We always quote that we're 70% defense focused and that we're 30% commercial focused, which is, as Rose said, where I live. We started off as a transducer design house in 1994, and I should say a transducer design basement, because our founder, Dr. Bruce Armstrong, who many of you might know, he started manufacturing hydrophones in his basement for the oil and gas industry after a storied career at DRDC, which then was DRDO, Ultra Electronics, and of course his academia career. In 2006, Bruce was joined by our president, Paul Yateman. And Paul and Bruce together, they really put GeoSpectrum on the map. We started designing more and more sensors for a variety of different applications, started to get into more technical transducers, and then, you know, in 2014, we acquired a company called Acoustics, which was actually one of our neighbors, so the move was very easy, I hear. And what they allowed us to do is move out of the realm of being a transducer and component supplier and into the field of system sales and system design. Because in order to do that, you really need to be able to, in order to manufacture systems and design systems, you need to be able to put intelligence into those systems. Otherwise, they're just basically sensors in the water. So now we have the capability in-house to do all of our mechanical engineering, electrical engineering, software engineering, and integration engineering to bring all those components together to manufacture large defense systems and commercial systems for navies and for, you know, marine research institutes. So Acoustics was a signal processing and software company, and they've really helped us. Kind of move into the system-based manufacturing. Of course, we still cater widely to the commercial industry. I wouldn't have a job if we didn't, I guess. So right now we're actually 80 employees, and we're growing very rapidly. I started with GeoSpectrum back in 2017 on a work term, actually, and from then, well, we were 50 people then, and now we're 80. So, you know, 30 people in 3 years is pretty substantial. So one thing that I really believe in, and management and believes in as well, is taking good care of the companies that are our backyard. So companies that do need our transducers, our sensors, sound sources, hydrophones. It's my belief that if you don't take care of the folks that are in your backyard, you're not properly going to be able to cater to the folks internationally. So we've been a proud supplier of Ocean Sonics since 2012, maybe even earlier than that, but that well predates me. So I don't know, I'll have to let other people kind of chime in if that date is incorrect. And you know, we really truly have an international footprint. You know, it's exciting being an international business. You know, I get emails every hour of the day from different places in the world, you know, speaking to people from Australia, and of course that time difference is staggering, you know, and I'm waking up, they're going to bed. It's challenging to kind of get on the same page. Cultures are different. But it's so exciting, and I'm very happy to be a part of it, especially in this sector. You do a lot of travel. Well, we used to do a lot of travel before COVID hit, you know, to London, all over the States, into Europe, Asia. And, you know, it's been a big departure from that this year. Of course, all the trade shows and whatnot have been postponed or canceled. And so it's great to be able to talk to you guys today through this forum and flex my outside sales ability, because it might be a little bit have atrophied a little bit, and if it has, I apologize, but that's just the situation that we're in. So, summary. Today I'm going to talk to you guys about transducers. What is a transducer fundamentally? What types of transducers are there out there? What are hydrophones and sound sources? What's sonar? How is sonar used in the industry or used, you know, to collect data? piezoelectric ceramics. Of course, we wouldn't have sonar, we wouldn't have hydrophones or sound sources without piezoelectric ceramics. For the most part, there's some exceptions to that rule, but today we'll be focusing on piezo's. And of course, I'll get into the applications, the broad spectrum of applications that are out there for these sound sources and hydrophones and whatnot. So a transducer, what's a transducer? So boiled down, a transducer is a device that converts one form of energy to another form of energy. And we deal with them on a day-to-day basis all the time. So antennas, thermometers, LEDs, they're all forms of transducers. They're just not called transducers. Antennas can take iridium signals and convert them into electrical signals so they can be read and we can send data through that means. Thermometers take temperature and through the expansion of a fluid or through electronics that I don't understand can give us a readout of what the temperature is in the exact environment. Humidity sensors, light emitting diodes actually are transducers as well. And of course, so are hydrophones and sound sources, which is what we're going to be talking about today. Sorry to those who are interested in hearing about thermometers today. And I'd be remiss if I didn't explain what sound is, because it's the fundamental way that we put energy into the water and we take energy out of it. So sound, when you boil it down, it's a fluctuating pressure wave. And sound can be low frequency, have a long wavelength like the image you see above, or it can be high frequency, like the shorter wavelengths you see below. And I always like to compare it. I use two comparisons generally. If you tie a rope to a doorknob and you wave the rope up and down, if you do long sweeping motions, you're going to get low frequency waves in that rope. If you do it quickly and rapidly over short periods, you're going to get high frequency wavelengths in that rope. And another analogy I like to use is bells. Large bells, when you ring a large bell, you get a large kind of, more bassy tone that has a low frequency sound output. And of course, like a dinner bell, a small bell would have a high frequency input. And I'll come back to that later and compare it to how it applies to transducers. So sonar, sound navigation and ranging, that's where the name comes from. There are two main types of sonar. There's active sonar and there's passive sonar. Active sonar, basically what bats use to find food, to see one another, to see the world around them. It's what dolphins use in the ocean. It's a form of echolocation. So a submarine can use sound and bounce it off the hull of the ship to tell that there is a ship there, so they can take action against it if they wish. Of course, they can't see out of the periscope when they're at depth because light doesn't travel very far in the ocean. So we have to use sound to gain that information about our surroundings. That's active sonar. Passive sonar is, as the name suggests, it's passive. You're not putting any energy into the environment. All you're doing is taking energy in. So our ears, that's a passive system. So we hear an ambulance drive by and we know which direction it's coming from. That's an example of passive acoustics. And that's basically listening to sound, listening to the environment and gaining information from it. I always like to quote, we use sound to see in the ocean. Of course, the folks at Kraken might disagree with that because, they've got some pretty sophisticated lasers that they use to see quite well in the ocean. But for the most part, if you want to see over long ranges, you need to use sound. So light, as a rule of thumb, you get tens of meters in the ocean. Sound, you're going to get thousands of kilometers. And we actually did a test up in the Arctic there last September, where we actually got a positive detection range from one of our low frequency sound sources at 2,500 kilometers away, which if you go on Google Maps or Google Earth and you look at how far that is a staggering distance. So of course it's a low data rate for those who know about that, but 2,500 kilometers is no slouch. How we put information into the water and take information out of it is predominantly through piezoelectric ceramics and the piezoelectric effect. So basically, piezoelectric ceramic is a unique material that when it's deformed, it creates a voltage, it creates a current within that ceramic element. And when a current is applied or a voltage is applied to that piece of ceramic, it'll actually flex in kind with what kind of signal you're putting into it. So as you press down on ceramic, you get a voltage out of it. And as you pump electricity into a ceramic element, it'll actually flex. And that physical flexing of that ceramic is what puts that wave into the water. And it's totally akin to what you're driving the ceramic with. Now, just full disclaimer, GeoSpectrum Technologies does not manufacture ceramic. We get ceramic elements from a lot of excellent suppliers, some of which are in Canada, and we use that ceramic as building blocks to build our sensors and systems. So piezoelectric ceramic is made out of three main elements and compounds: lead zirconate titanate, also known as PZT. As you can see in that top image, it comes in all shapes and sizes, and the shape and size of the ceramic really plays a large factor in what kind of frequency it resonates at, and what kind of sound it puts in the water, the power that it puts into the water. And you know, below there you can see lead, zirconium, and titanate. Those are the three main compounds that go into it. So according to Pi, who is a supplier of piezoelectric ceramic, these are the stages in which we manufacture ceramic. So there's a mixing and grinding of the materials that I mentioned before. It's fired in kilns at great temperatures, so around 1,000 degrees Celsius. There's a mechanical milling procedure to kind of, you know, hew it down into the shape that you're looking for. There's a drying phase. Again, it's pressed into a shape that you want it in. And ceramic elements come in again in all sorts of different shapes and sizes that, you know, have different advantages and disadvantages. And I'll get into how that applies into hydrophones and sound sources in a little bit. And then there's another firing stage, which I guess kind of sets it even further into its final shape. And a machining phase where you kind of, you know, hew it down to what the final product's going to be, and then you apply and you provide an electrode to it. So basically, a place to hook up wires, and then wires to the ceramic element, and then you polarize that ceramic element by pumping current through it. So the size of the ceramic elements that you're using will dictate its resonance frequency. Now, what does that mean? So back to the bell analogy. A large church bell will make a lower, louder sound than a small little bell. What that means is ceramic elements have different strengths and weaknesses depending on their sizes. If you're trying to put a low frequency sound into the ocean, you're going to need, as a rule of thumb, a large piece of ceramic, or you're going to need a lot of smaller pieces of ceramic that basically equate to a large piece. And vice versa. If you want to make a high frequency sound and you want to transmit high frequency signals, you need a smaller piece of ceramic. So we take those piezoelectric elements, those building blocks, and what we do at GeoSpectrum is we manufacture sensors around those. So we manufacture streamer hydrophones, you see up here on the top left. This is simply a ceramic element encased in a potting compound, a goop, and then it's wired. So basically, that innate response to that ceramic element is what you get. There's no electronics in it. And for the most part, these sensors are put into larger sensors. So they're put into towed arrays where there's, you know, 8 or 12 or however many elements in them, and they're put into custom designs too. We have a company that we deal with in the UK that actually uses these hydrophone elements in an instrument that will tell the user how much flow is going through a pipe, and they're used in the like London, England's water supply, so that they can tell if things are all acting as they should be, and if they're not, then they can figure out exactly which station is creating the error, and they can go in and fix it. This hydrophone here, this is a preamplified hydrophone. So basically, that adds an electronic stage to the one I just mentioned. So that guy has you know, a piezoelectric ceramic element in it. It's wired to a preamplifier, and then it's got a connector, and it's basically just in a ruggedized body so it can survive the harsh ocean environment. And then, of course, to the far right there, we have the IC Listen Kayak, which is one of Ocean Sonics' newest hydrophones. We're very proud to be able to provide them with the hydrophone element, the sensing element for that hydrophone. And those are a few kinds of hydrophones that are in the world, you know, streamer hydrophones, preamplified hydrophones, and digital hydrophones like Ocean Sonics is so good at making. As far as sound sources go, remember, if you switch the ceramic over and you're actually applying a signal to the ceramic, it's going to flex out, it's going to flex, and it's going to disturb water, and it's going to put sound into that water, pressure waves. So from left to right, we have the IC Talk, which is another Ocean Sonics product. Basically adds intelligence to a rudimentary sound source and allows you to have more control over the information you're putting into the water. The transducer with the red locking sleeve there, that is a communications transducer. They're used for two-way comms. We sell those in bucket loads to companies like or institutions such as like Woods Hole Oceanographic Institution. They use them on their AUVs, on their gliders, on their subsea modems. And then we have spherical transducers of several different sizes there. So this graph, the plot here shows the affinity of a particular type of transducer to a bandwidth. So there's no end-all be-all transducer. They all have strengths, they all have weaknesses, and I'll move from right to left and explain them. So spheres, like you saw on the last slide, we manufacture all different shapes and sizes of spheres. They're really handy because, well, they're high-frequency transducers, and because they're spherical in shape, they're actually really resistant to pressure because of, you know, that shape actually it resists pressure very well. But unfortunately, they are air-backed, so they can't go unlimited ocean depth because eventually that air will compress and it will collapse on itself at a particular depth, depending on the size of it. Spheres are omnidirectional, so when a sphere is being driven, it actually puts sound out in each direction equivalently. So it's not, there's no beam width. It's not shooting like a flashlight or a spotlight signal. It's radiates from all around it. Tom-Pilz transducers, they're a pretty niche product. And they look like, well, they kind of look like a big water bottle, I guess. And what they do is they have transducers on one end of them that basically push a plate out, and that's more of like a spotlight beam pattern. They're predominantly used in hull-mounted sonars for the navies. Free-flooded ring transducers are mid FFRs, pardon me, are mid to low frequency transducers that are good for full ocean depth. So they have a couple different resonance frequencies, so they're good over a fairly wide band. They're great for communications, and you know they're really key because you can go down to 6,000 meters with them, no problem at all if they're manufactured right. MPSs, modular projector systems, are actually comprised of the one below that, several different benders. And benders are pancake-sized transducers that radiate omnidirectionally. They're air-backed as well, so unfortunately they have a shallower depth rating. And then MPSs are actually stacks of these different transducers. And then we get into C-base and the boxer, but those don't have piezoelectric ceramics. I'd be happy to come back another time and speak about those in more detail. So two different kinds of hydrophones. We have unpreamplified hydrophones and preamplified hydrophones. So this is an example of an unpreamplified hydrophone. This is a hydrophone assembly that we are lucky to make for Ocean Sonics. So it's comprised of two main parts. The ceramic element, which is the acoustic center of the hydrophone. And of course that's in a rubber boot, and it's got a potting compound that actually is filled within that boot to make it, to get all the air out of it so that it can survive depths, and so that it keeps it rugged and keeps the seawater out of it. And that's attached to a bulkhead with wires, so Ocean Sonics is able to screw it on their housing and do all the black magic that they do that I don't fully understand with the digitization of the signal and all the intelligence that they pump into it. So yeah, you have the threaded bulkhead with flying leads on the other side, and it's a titanium base plate. So because there's no electronics in this hydrophone, you're kind of at the mercy of what that ceramic element is. And you can put a sphere in there, you can put multiple different types of spheres of different shapes and sizes, you can put a tube in there, you can put something called a stripe tube, and it's going to change the response of that hydrophone. So in this particular hydrophone has a particular type of ceramic that gives it the response that's in the graph on the right. So that response is what it is. You know, if you want to change that, you need to change the ceramic element that's in there. Ocean Sonics is able to change things about the response by adding gain inside of it and all this other good stuff. I'll touch on that in the next slide. But for this hydrophone here, you've got on the y-axis, you've got receive sensitivity, which is measured in dBV per 1 micropascal. That's decibels per volt per micropascal. And then you see that its straight line runs from -200 dB all the way across till about 10 kilohertz. It's actually about 3 kilohertz. I think it starts to kind of drop off a bit. So that's its response that it's going to get. So the x-axis has, it's got frequencies from 10 hertz all the way up to 200 kilohertz. So if you look at that response, if this hydrophone sees a signal at 10 hertz, you're going to get -200 dBV out of the other end. if it sees a frequency of 1,000 hertz, you're still going to get minus 200 dBV out. So it's a very flat response, which is very desirable within the industry, because basically from a wide bandwidth, you know exactly what you're going to be getting for receive sensitivity and for an output. So to kind of step things up a notch, we have preamplified hydrophones, and we add an electronic stage to this to kind of change the response of the hydrophone, to customize them more to our customers' expectations. So once again, you've got the ceramic element, the acoustic center of the hydrophone. This time, though, you have a preamplifier housing with, of course, a preamplifier within it, and then there's a subsea connector on the other end, or you can put flying leads on the other end. So preamplifiers allow for the customization of the output signaling type. You add gain at that stage, and you add signal filtration. So some common filtration or some common output signaling types are single-ended voltage, differential voltage, and current. And gain levels, we provide them from 0 to 35 dB, but I'm sure there's other suppliers that can attain higher gains than that with different preamplifiers. So I'd like to talk about gain for a moment. So I like to explain this with this analogy. So turntables and record players and vinyl, it's making a resurgence right now. A turntable, basically what it is it's a stylus. It has a diamond tip on it, and the record player plays a vinyl. It spins a vinyl record around. That stylus vibrates a certain way depending on the sound waves that are etched in that vinyl, and then the cartridge of the record player creates a signal in that depending on the vibration. That signal is so small, it's a trace voltage, and that signal is not high enough to be able to be, read or recorded by a traditional commercial off-the-shelf COTS equipment. So what happens at the next stage of a turntable is you have a preamplifier, and what that does is it applies gain to that signal to increase it. So essentially, gain is just turning the volume up on your hydrophone, just like you would on your turntable, just like you do on your stereo or digital stereo. And for a lot of you that have home theater systems, oftentimes the home theater system actually gives your output of the sound level in dB. So, it's odd, you turn it on, it says minus 200 dB. And as you turn it on, of course, it goes up to, minus 190, minus 180. But that's really what gain is. It's increasing the volume of the hydrophone. So if you see a signal that's 200 dB, and I thought this is a funny little GIF. It's the most inconvenient volume increase toolbar of all time. So preamplifiers. So on the top left there, you've got your regular plot of the ceramic of the unpreamplified hydrophone that you saw earlier. So and that's got a sensitivity of minus 200 dB. That's how we'd advertise it. So by applying 35 dB gain at the preamplifier stage, you actually increase the sensitivity to minus 165 dB, making that hydrophone more sensitive. So if you're trying to listen for something that's a very minute signal, or it's very far away, then you can pick it up easier by turning the volume of it up, by increasing the gain. So preamplifiers also, in addition to you being able to choose what signaling type you like, you can also add bandpass filters, and this is where you really customize a hydrophone, and you manufacture towards a customer's requirement, their use case. And the next slide, I'll get into that a little bit more as well. So bandpass filters, or minus 3 dB roll-offs, is as the minus 3 dB roll-off suggests, it's where the signal is actually down by 3 dB on either end. So in this particular plot down here, we've got a 100 hertz low frequency roll-off and a 50 kilohertz low frequency, or high frequency roll-off, pardon me. What does that mean? Well, this is an application for bandpass filters. A lot of you folks, I'm sure, are keen on marine mammals, as am I. And marine mammal detection is a very big field in the oceans tech sector. Mapping out the migration routes of whales and learning kind of the effects that all the sound that we're putting in the oceans having on them is a big field. It's an important field. So in this scenario, we're listening for sperm whale clicks, which have frequency ranging from, they put energy in the water from about 1 kilohertz to 10 kilohertz. And then dolphin whistles, which is from about 1 kilohertz to, let's say, 12 kilohertz. You marine mammal detectors out there might think I'm off a little bit, but feel free to leave some comments if I need to adjust these a little bit. So you're listening for dolphin whistles and sperm whale clicks. The only problem is there's a drill platform close by. we know through all the research that we've done at the DFO and all these great institutes and companies do that drill platforms have put sound into the water predominantly from 10 hertz to 100 hertz, right? So by adjusting our bandpass filters, by adding a low pass filter or a 100 hertz low frequency roll off, we're actually able to nullify that whole end of the bandwidth. So we don't hear the drill platform. All we hear is our dolphin whistles and our sperm whale clicks. All of that noise that would be our drill platform, the drill platform, is not showing up in our signal at all. So we're essentially deaf to that drill platform. So we can get the data that we want from the dolphins and the sperm whales. And of course, the high frequency roll off would roll the high frequency end of that off as well. As far as sound sources are concerned, there are two kind of main channels that we'll provide to customers for sound sources. There's the one-way sound source where you have a signal generator. So think about the record player example again. You've got that needle scratching the record, a very small voltage. An amplifier will step that up through a step-up transformer, matching inductor, and then that more powerful signal will be applied to the transducer. And if you remember from earlier, having these signals pumped into ceramics actually cause these ceramics to physically expand and contract, and that will put a wave equivalent to what you're putting into the amplifier into the water. So that's one way. So you're just talking with that. This is an example of a transceiver. So this system here can actually send sound into the water. It can talk and it can receive. It can listen as well. So to go left to right again, we've got a data logger that will receive the data. We've got a transceiver that can actually send or receive signals, and then we've got the transducer. So the transducer, when it's in talk mode, it's going to be putting a signal into the water, and then the transceiver can switch it into a listening mode. And then if it's going to get a return off of, let's say, the hull of a submarine, then it will enter listening mode. The sound will be absorbed into the transducer. It'll go back to the transceiver and get logged or get processed in real time. Sonar operators aboard destroyers and surface Navy ships, they look at all this data in real time, and they're looking for submarines using a variety of different transducers on systems aboard a ship. Hull match sonar being one. So a submarine operator, a sonar operator, pardon me, is actually sitting at a console looking at the sound that's coming in and looking for returns or for sound signatures that they studied and that they know to be, oh, that's the blade rate of a Kilo class submarine, or oh, that's what it sounds like when coolant fluid's rushing through the cooling pipes of a nuclear submarine. And to cap this all off, I'm going to list a few of the very many applications that there are in the oceans in the marine acoustic sector. So there's three main predominant categories of research and of work in the sector. Environmental, as we mentioned before, marine mammal detection, listening and tracking marine mammals, learning more about them, learning more about what harms them, and where should we change our shipping lanes to, what should we make a protected area if we know that there's a mating grounds for a particular species of whale. DFO can gather that data and make the call, okay, thou shalt not have marine traffic in this area, and they'll police that. So the more information we can pull out of the environment, the better we're going to be able to help these animals. Noise monitoring from subsea construction all the way to shipping lane, noise monitoring to listening to a Navy sonar going off. It's important to understand the impacts we're having of the sound that we're putting in the water, and by listening to that and studying the impacts again it has on mammals is a very, very important field. Bathymetry, side scan sonars, multi-beam or side scan sonars, multi-beam sonars, synthetic aperture sonars, they all use sound and high frequencies to actually map out the ocean floor. So it's much like topography. They use lasers from planes. We use sound underwater, and we use sound to see in the ocean. Biomass estimation. So we can use sound and actually reflect sound off of schools of fish to get an idea of how many there are, how well the stock's doing that year, and DFO can take that information and they can say, you can't fish this type of fish this year because the population is in an unhealthy state. And wave measurement, you can learn physical attributes of the ocean by listening to the ocean. In the oil and gas sector, you've got seismic surveying. So right now, oil and gas seismic survey companies, well, maybe not right now because the oil and price of a barrel of oil leaves much to be desired. But seismic surveying companies, they actually go out in the ocean and they have what are called air guns. And air guns put an explosion of water, explosion of sound into the ocean. It's basically a depth charge essentially, and that sound travels down to the seafloor and it reflects off the seafloor and it refracts off of the strata that's in the seafloor. And through fancy post-processing that I don't understand, they can determine if there's oil in the ocean or not under that area. Sub-bottom profiling, similar to seismic surveying, it basically provides you with more high-resolution data of what the bottom type is and what the layers below the bottom are made of. And of course, that sound source example I provided earlier, communications. Communications is a huge field in the oceans tech sector. It's used in the environmental, oil and gas, and defense industries across the board, and we are making great advances in it. It's challenging sending communicating data through the ocean. There's a lot of factors that come into play, weather, salinity of the water, temperature, depth of the water, that all come into play in this, and it's a very challenging field, and there's a lot of exciting work going on actually in our backyard here. In the defense sector, of course, anti-submarine warfare, ASW, we use it to track and to find submarines in the ocean. Intercept sonar, higher frequency sonars can be used to track and detect torpedoes, and then the vessels that are listening for it can actually take action to get out of the way. Mine countermeasures, you can use sound, you can use side scan sonars, multi-beam sonars to find mines, subsea mines, and to deal with them in an appropriate manner. And of course, we use them to navigate in the ocean. Submarines can't see very far in the ocean with the periscope, so they use sound to do so. And there are a lot more applications that haven't listed there. I could talk to you about it for hours. So, and with that, thank you very much for your attention. And I'm happy to field any questions that you folks may have.
I'm going to leave this last slide up for a second. So if anybody wants to grab Matt's email, I'll just let it hang out there for a moment, copy it down quickly. Otherwise, I will put it in the show notes. So if anybody does have questions for Matt, then either ask them now or you can send them to him directly. By the way, so if you have questions, I have plenty.
Fire away. I'll try my best to answer them, and if I can't answer them, I will go to the engineering team and I will ask them for answers.
Fantastic. First off, I just want to let you know, I absolutely loved that explanation of the bandpass filter.
Good. Yes, I'm happy you did. I was trying to figure out
the concept that sometimes is difficult to grasp when you're just trying to explain it, but I love that diagram. It was fantastic. And of course, gain settings. I mean, what a great explanation. I always talk about adjusting the sound of my stereo.
You're doing it. You're adding gain, or you're adding attenuation, which is actually the opposite of gain.
So I did want to let everybody know, watching the presentation, if you're interested in asking a question to Matt, you can leave the question on any of our social feeds right now. We are watching them, so we will answer them live as best as we can. So we have an interesting question here from our YouTube feed. Why do you have to remove air from the housing around a piezo element? If air is still there, how does it affect the recordings? That's
an excellent question. So to answer the first part of that question, air actually compresses in the ocean. So think about, I'm not sure if you've seen it before, but if you take a styrofoam cup and you put it in a pressure vessel that goes down to the seafloor, or you put it into a pressure vessel on land that actually applies pressure for testing, and you jack that pressure up. When you pull that styrofoam cup out of the water, it's going to look exactly the same, but it's going to be ridiculously small. So that's what happens when you have air in something. It actually will compress under that pressure by removing all the air and by having a solid potting compound, protecting your hydrophone. It actually will, it won't compress as much when it's going down the seafloor. Of course, if you have a 1/4-inch sphere as the ceramic sensor within a hydrophone, there's air in that sphere, but because that shape is a sphere and it's very resistant to pressure, it's actually going to go down deeper than it would if there was air trapped in the potting. And it also introduces leak paths. So if you're going down and you got air bubbles that are popping within your potting compound, water will find a way to get in. As you know, people that are experienced in the industry deploying ocean equipment are well aware the ocean will find a way to get into your sensors, and you need to take the utmost care to make sure that doesn't happen. And as far as what the effect it has on the sound itself, it can be totally devastating. You know, we do all our own calibrations here at GeoSpectrum using, you know, our in-house designed calibration equipment. If we can't do them in-house, it's too low frequency because the wavelength's too long, we have to go into the harbor, and we do it out in the Halifax harbor. If we have too much air in a transducer, in an oil-filled transducer, for example, it'll actually totally alter the response of the transducer itself. And it's plain as day when you're checking it out in the calibration data. If our modeling does not agree with it, then there's something wrong with it, and chances are that its air has found a way to get into it. And it's tricky when you're oil-filling sensors because you need to take great measures to make sure that the air actually finds its way out. And of course, it's a blind process. You can't see inside of it, so you're just kind of hoping for the best that it's all out. So I hope that answered your question.
So I have a question for you.
Yes.
What's the major difference between directional and omnidirectional hydrophones? And can you turn an omnidirectional hydrophone into a directional hydrophone? Okay,
great question. So omnidirectional hydrophones and directional hydrophones, as the name suggests, but it's not totally clear. Omnidirectional hydrophones, when you're listening through one, and it say a whale is 100 kilometers away, and you hear that whale, okay, you know there's a whale in the vicinity, but you don't know where it's coming from because there's no directivity in it. It's omnidirectional. If you have a directional sensor and you hear that whale, you go, oh, there's a whale in the environment, and it's that way. You know, it's 50 degrees in that direction, right? So directional sensors literally give you directivity out of the data you're getting. And omnidirectional sensors will tell you information about what's in the ocean, but you don't know exactly where that's coming from. Now, there is an exception to that rule. If you increase the amount of omnidirectional elements, let's say you make an array, an 8-channel array, so 8 elements, 8 omnidirectional hydrophone elements, you can actually get directivity out of that. And this is where it gets complex. So it plays into the phase of the sound that's coming into the transducer and the way that the ceramic elements are wired up. So basically, think about having an array of hydrophones, horizontal array, and you've got something that's 90 degrees to that array. If that thing makes a sound and it hits that array of 8 elements, if the sound is going to hit, it's going to take the direct path first. It's going to hit those first elements in the middle first, and then it's going to hit the other ones last. So through post-processing, you're able to determine, okay, there's a vessel over that way because, we know that these ceramic elements were energized before these ones, and you can tell that it's coming from a particular direction. It gets more complex when you start talking about left and right ambiguity, because if you think about it, if you have a bunch of omnidirectional elements in a row and you've got a boat up here that makes a sound, what's the difference going to be from a boat down here? They're omnidirectional. You're not going to know, right? So that's left right ambiguity problem. You don't know which side that boat's on. So through more things that I don't understand, we're able to determine through post-processing, through the phase relationship of what the sound that hits these elements, which way that's coming from. And you can get even fancier. You can add NAS sensors to your equipment, so non-acoustic sensors, we call them. So you can put a compass in that array. Right, so now you have a reference point that is that array. Because if you think about it, if you didn't have that compass in it, you need to know exactly the orientation of that array when you put it in the water, or you wouldn't. Your directionality would have no bearing. No pun intended. So by having a compass on that array, you know where that array and you know what direction it's facing at all times. You can tell where that array is. You can tell where that boat is going to be.
So you touched on it during your answer, but can you give an example of when might someone want to use a directional versus an omnidirectional hydrophone?
Yeah, for sure. So if you're it depends on the information you're looking for. So a scientist, a researcher, if they're keen on knowing, I need to know if there's right whales in this region, stat. You can put an omnidirectional pressure sensor, into the ocean, which are cheaper than direction sensors. They're less complex. There's less parts to them, and you can tell. Okay, I got my data. I know that I've heard calls from several different targets. I know that this area is a hotbed of activity for right whales. And then maybe that one researcher goes, okay, now I want to know where they're going. I want to know where they came from. I want to know what their behavior is. So then you can put directional sensors in the ocean, and you can find out basically more granularity on the behavior of those animals. And there are plenty of examples you can use. You know, you can apply that same idea to the defense sector. You know, you're looking for submarines. You know, do you want to know if they're generally in the area, or do you want to know exactly where they are? You probably want to know exactly where they are.
Sounds like something you might want to know.
I think so, depending on who it is, I guess.
So in your presentation, you showed both passive and active acoustics. Yeah. Is there a time when you want to use those together?
There is. Yeah, so, and I'll give two examples of this. So the transducer example that I gave, the communications transducer example, you can have, let's say, a 2-channel system. So you have one of those free flooded ring transducers with a transceiver on one end it transmits and receives, and you can have another one on another end. So basically these two nodes can pass information between one another. They both have the capability to send and receive. And you know, you'd want that. I can give an example, you know, a GeoSpectrum example for that. So we manufacture a particle motion sensor, which is another form of directional sensor for the low frequency bandwidth that you place on the seafloor, and it logs data for 20 some odd days. Well, when you deploy something to 1,000 feet of water, 1,000 meters of water, you have no idea if it's going to be sitting flat on the bottom or if it's like this, you know, on the side of a slope. So we created something called it's a two-way communications check. So basically what that does is there's an RPY sensor within the electronics that will, you know, create a signal within the system that will send a sound signal up to the surface that says, hey, I'm good, you know, I'm not upside down. And then the same sensor will actually put a sound in the water that says, lift me back up, reposition me, move to another station because I'm you know, not in a good way. So by having that ability to communicate back and forth, so the folks on the sea surface, they can send a prompt down to this system and say, how are you? And then the system can say, I'm good, or help me, kind of thing, right? So that's an example of a two-way communication system. Another example is bistatics. So if I'm a transducer and there's a submarine, you know, swimming by me, or, you know, moving by me, you know, I can either send that signal out, bounce off a submarine, or hope and hope that I get a response. If I'm another submarine, I don't want them to know where I am by any means, right? Because the last thing a submarine wants to do is come to the surface and be seen, and the second last thing it wants to do is make noise so other submarines or destroyers can see where it is. So what you can do is you can do something called bistatics, where you have an installation, say a surface vessel that drops a depth charge off of the vessel. That depth charge explodes. The sound travels to the water, it bounces off the submarine's hull, it reflects out, and it gets picked up passively by a submarine. So that way the submarine is gaining intelligence. It's not putting any sound in the water. It's not saying, here I am. And it can actually act accordingly to that. And you can gain some very valuable intel from it.
I love the idea of like a two-way wellness check from a couple of ocean robots.
Yeah. Well, the way the sensor is deployed, it's the utmost importance that it's straight, not perfectly flat. Of course, that's, you know, close to impossible. But you know that it's within a certain realm of you know, cockness, I guess you could say. But if it's like this, then the sensor that's hanging down is going to come into contact with the frame, and you're not going to get any good data.
So there's a really interesting question that just came in on our YouTube channel, and I hope you can take a crack at this.
I'll try my best.
So, is it possible to combine the data from two arrays to provide a triangulated position for the target?
Gather information from two arrays to triangulate information from the target. Yes, it is. Yes, it is. And it's a more, and I can't get into total detail on this because I'm not an engineer, but basically, if you've got two arrays with a known spacing away, we're actually talking to a customer with this right now. So if you have two arrays that are being towed at a known distance away, and you can keep those arrays pretty much the same distance from each other, essentially you're adding more array gain to the system itself. So you've got more elements in the water. So basically it'll solve your left-right ambiguity problem, because, you know, one array is going to see that sound if it's coming from, let's say it's coming from the right side. One array is going to see that sound well before the one on the left, in terms of, you know, data processing. So you're going to be able to tell, you know, what direction that target's coming from, and you know, through processing that data, you'll be able to get a better bearing on it. because you've got more sensing elements in the water.
So I have another question for you. So I'm not an expert in underwater sound sources. I'm more on the passive side. Can you explain to me what someone would use a specific sound source for, like a sphere versus an FFR or an MPS?
Yeah, absolutely. So we deal with this on a daily basis. So really, it comes down to the first question that I ask is, what frequency bandwidth are you operating in, right? If it's on the high end of the spectrum, a bender, which puts sound in a low frequency, isn't going to be appropriate. A sphere would be. So let's say it falls right within what a sphere can do. Spheres have their limitations in that. So if you wanted a transducer to operate up at 100 kilohertz or 20 kilohertz, you're going to be using a sphere, but it's going to be omnidirectional. So there's trade-offs you need to make. There's no perfect solution to any problem in the when you're talking about marine acoustics. So spheres are good at a moderate depth. I think they're good to like 1,000 meters. I might be mistaken on that. So if you need to go down deeper than 1,000 meters, we're going to need to re-engineer this sound source for you, or you're going to need to play with your requirements a bit more. As we move down, we might be able to manufacture a free flooded ring, an FFR transducer. They don't have any air in the system. They're totally encased in oil, and they're good for full ocean depth. The only problem is that they're more suited for mid-frequency range, but you can make those transducers smaller to make them higher frequency, and through some back and forth and some clever engineering, you might be able to come up with a solution, a new product that will fit the requirements. It's just a matter, it all comes down to what is and what isn't physically possible. You're balancing a lot of different aspects of physics when you're talking about putting a transducer in the water. The frequency that a particular sound source is going to resonate at is one. Some transducers have an affinity toward one bandwidth than others. Depth requirement, benders, those flat pancake transducers, they don't survive particularly deep, but they put in high power, low frequency. And FFRs, they put in moderate power over medium frequencies, but they're good to full ocean depth. So it's a balancing act and compromise to find a particular solution for your scenario.
So I have one more question for you.
Sure.
And this is a bit of a pie in the sky kind of question. Yep. But what would you like to see as far as technology developments in underwater acoustics? What do you want to be able to do next?
That's a really good question. I'd have to say better data rates and better data throughput reliability. So, there are a lot of factors that come into play in how your communications, how your data is being transmitted to the water. One is that because, acoustics are kind of on the lower spectrum and they're not, in the hundreds and thousands of kilohertz like other things, you're not able to transmit as much data through the ocean, fundamentally. You can with some laser systems in the ocean, but through sound, it's much more challenging. So there's a lot of companies out there that have actually come up with some really clever ideas on how to increase that data rate and how to increase the reliability of the data, because it's, an ocean environment off the coast of Nova Scotia would widely vary from the Mediterranean, let's say. So the way the sound propagates in the water there would vary widely. And, weather systems and whether the rain has just fallen, and temperature of the water, what season it is, where the thermocline is, which it's like all these things come into play, and they can either make your life miserable, or you can use them to your advantage. So what I'd like to see is a higher data rate, so we can transmit more data in situ, so we can send more high resolution images. Video would be great, and to be able to increase the reliability of that signal. And there's some really interesting companies here in this area that are working on that very thing right now. At Cove is a company called Maricoms, and they're working on a very reliable, robust communications protocol for the ocean. And we're actually, they were going to show it off at the H2O conference this year, but unfortunately that got canceled, or postponed, I suppose, till next year, you could say. So hopefully next year we'll see that from Maricoms and their team.
That's something to look forward to.
Oh, definitely. I can't wait to get back to another trade show. I'm looking forward to it.
So I guess that's something else you'd like to see coming up in the near future.
I should have said that. That's exactly right. Yeah, I'd like to go to London again, please.
Well, it looks like those are all the questions that we have for now. Again, thank you so much for joining us today, Matt. If there's a question that you didn't get to ask, or if there's a topic you'd like to see covered during this web series, please contact me by sending Ocean Sonics a message, or you can always drop us a line on any of our social feeds. Matt and his team at GeoSpectrum can be found through their website, geospectrum.ca, or on their social channels. And if you'd like to revisit this presentation, it will be available on both YouTube and Facebook, and I will share the link through the other social feeds that Ocean Sonics has. Thanks again so much to everyone for joining us today, and hopefully we'll see you next week for another live session.
Thank you very much for your attention, everybody. And thank you, Rose and Ocean Sonics, for having me. It's much appreciated.
Anytime, Matt. We'd be happy to have you back if you ever want to talk some more transducers.
Sounds good to me.